Welcome friends. So we are discussing network theory. Already we have finished 7 modules. Now we shall start shortly module 8. Now this module is the introduction of Laplace transform. This technique is very useful to solve the transient behavior of the electrical network. Now we have already seen one approach of solving transient response of electrical network using differential equation approach, which is mainly time domain based. Now we shall go through, or we shall explore another option to solve the network problems using frequency domain approach. Now to solve those transient response problems using frequency domain approach, we have Laplace transform technique. It is extremely useful technique to solve this kind of problem. So this module is mainly we shall focus the introduction of Laplace transform, and later on in the next module we shall see the application of Laplace transform in solving transient response of different electrical network. So let us going straight to the topic, which is called Laplace transform. Now, based on this transform, any time domain signal can be converted to its frequency domain signal with this help of this example, with this equation. Sorry. So, if we have a time domain signal ft, then if we apply the Laplace transform of Laplace transform on this ft, then this function will be a function of s, that is in the frequency domain. So here t represents time domain data and s represent frequency domain data. What is this s? Now s is equal to sigma plus j omega. Sigma is called Nepper frequency. Sigma is called Nepper frequency, and it should be unit. It should have unit Nepper per second, and omega has the unit. It's called angular frequency. It's called angular frequency. It should have a unit radian per second. Now, when this Laplace transform is applied, then this Fs will be mathematically equal to Ft. Then you should multiply it with this operator e to the power minus st. Then you should take the mod, and then you should take the integration from 0 to infinity. So it will give you the Laplace transform of ft. So this is the equation. This is the equation, fundamental equation of Laplace transform, definition of Laplace transform. So you have a term or operator called s. On applying with the time domain function ft, it's multiplied with e to the power minus st. Then you should take the magnitude of that product, and then you must carry out the integration from 0 to infinity. So this is the definition of Laplace transform. Now let us quickly going through some few important properties of Laplace transform. The first property is like that. So we Assume that if a function is in time domain is ft, now if you apply Laplace transform on ft, then that function will become fs. Now the first property is saying that multiplication by a constant t, by a constant k. Now if that same function ft is multiplied with a scalar by k, then its equivalent Laplace transform will be k into fs, that is number one property. We shall see the application of this property very soon. Let us discuss them one by one. Now the second important property is that sum and difference. Okay, so let us say we have suppose we have two functions. First function is f1t, its Laplace transform is f1s, and we have a second function is f2t and its equivalent Laplace transform is f2s. Then if a function is defined by ft is equal to f1t plus f2t, so its equivalent Laplace transform will be that is ft, its equivalent Laplace transform will be f1s plus f2s. And it will be true even for subtraction. So if ft is f1t minus f2t, then its fs will be f1s minus f2s. So this is the property of summation or difference. Now third rule is very important. It is the differentiation rule. It's very, very important. So if we have a differentiable function dft dt, then if we apply the Laplace transform of the differential function, then the result will be sfs minus f0 plus. It's an extremely important property. So if we apply Laplace transform of dft dt, then you will get s into fs, that is okay. Additionally, we will have a constant term f0 plus, and this term comes from the initial condition. We have already explained the significance of 0 plus. Okay, it is just after the switching. It denotes just after the switching, which is coming from initial condition. Now what is the application of differentiation rule? Know that that is voltage across the inductor. Voltage across the inductor is L di dt. So now if we apply the Laplace transform technique on this equation, so here you see there's a differentiation comes. So if you apply the Laplace transform technique on this equation, it will be simply L into SIS minus I0 plus. So it is the application of this rule. It is since this equation is already described previously, so I am directly giving you an example that application of this differentiation rule on the network analysis circuit. So we have V is equal to L di dt, that is voltage drop across the inductor. So the Laplace transform of this technique, or if we apply the Laplace transform on this equation, this di dt becomes this as per this differentiation rule, SIS minus I0 plus. So it is again what is I0 plus? It is the current flowing through the inductor just after the switching. Now similarly, we have an integration rule. So if we have an integration like this, L Laplace transform of ft dt, integration 0 to t ft dt, so we can apply the Laplace transform rule that it becomes Fs by S, simply Fs by S. So you can get a direct application that what is the voltage drop across the capacitor. The formula is 1 by C integration 0 to t it dt. So you see, this is the integration, exactly it is matching some expression of current, some function of current is it. So you see, it is exactly matching. So if you apply the Laplace transform of this Laplace transform on this equation, then it will simply becomes Is by S, and we have additionally 1 by C with us. So this is the direct application. So in this way, differentiation rule and integration rule is extremely important. We shall apply in appropriate time. We shall shortly see. Now rule number 5 is also very important. Sometimes let us say we have a function like this. Let us say it is this function, okay. In x-axis we have t, in y-axis we have ft. Now it starts from 0. It starts from 0. Now instead of starting from 0, if that function starts from some other points, right? If it starts from some other point, let us say t is equal to some other points A. So actually what it happens is that it is actually shifted. It is the signal, the same signal is time shifted. If the same signal, the same signal is time shifted by this amount, by this time amount, t is equal to A. So exactly this rule, the rule number 5 is exactly this, it is to highlight this property that any function is shifted in time domain. If any function is shifted in time domain, then if we apply the Laplace transform, then it will be multiplied in the frequency domain. So you see, this is the shifting parameter t minus a, then this same amount will be multiplied in the frequency domain with the exponent term e to the power minus as. Okay, ft is fs. Okay, the Laplace transform of ft is fs. Laplace transform of ft is fs. Now what is t minus a? T minus a is the time shifted. So that time shifted is reflected in the Laplace domain on frequency domain by this factor e to the power minus as into fs. So basically the shifting rule is that if any function is observed to have some time shifting, then if you apply the Laplace transform on that function, then in frequency domain it will be multiplied by a exponent factor e to the power minus as. That is the shifting rule. Now the next rule is just the reverse. Rule number 6, it's, you see, it is the multiplication rule. That means now it is multiplied in, suppose we have a function ft. Now with that ft we have a exponent term, that means e to the power minus at, that means it is multiplied in the time domain. So time domain multiplication in the time domain, if you apply Laplace transform on this function, the result will be shifting in the frequency domain, shifting in the frequency domain, f into s plus a. So property 5 and 6, we can see two different things. If we observe time shifting in the, or if we observe shifting in the time domain, that means multiplication in the frequency domain. And rule number 6 is that if we observe some multiplication is in the time domain, then it Laplace transform, it is the shifting in the frequency domain. So it's a two-way property of the Laplace transform. Now equation 7 and 8, sorry, not equation, it's a property 7 and 8. It tells about the any function, what will be the value at its transient state and what will be the value of its steady state. That means if this is a function, if this is something a function, okay, then according to this theorem, initial value theorem and final value theorem, we can estimate or we can calculate, evaluate what is the function value at transient state. That means what will be the value of ft at t is equal to 0. That is called initial value. That is called initial value. And at this point, what is the function value? So what is the function value ft at limit ft tends to infinity? So this is called actually final value. So according to these two terms, we have initial value theorem and we have final value theorem. So if we apply the Laplace transform, then the relation is quite straightforward. So if we want to evaluate the initial value of the function, then it should be, you first have to multiply s into fs, then you put s equal to infinity. That is the formula of initial value theorem. And final value theorem, if you want to calculate the final value, that is t is equal to infinity, what is the function value, then it should be SFS, again the same formula, but this time you must evaluate it at s equals to 0. So these two are initial value theorems and final value theorems. Now let us discuss another very important property, that let us say we have this function. Let us say we have, suppose this function. Now what is this called? This type of function, it is called periodic function. Let us say time period is t. So it is repeating itself after a time interval of t. So now if anyone asks, then what is the Laplace transform of this entire signal? What is the Laplace transform of this entire signal? This theorem is telling you that you should not have to deal with the entire signal. Just you need to do the Laplace transform of the periodic function with time period t. What is that? You need to first consider the only first cycle. You need to first consider this cycle only. Okay. So you need to evaluate the Laplace transform of this cycle, first cycle. You will have some answer. Okay, you will have some answer. Then with that answer, if you multiply this term 1 by 1 minus e to the power minus st, if you multiply this term with the original answer of the Laplace transform of the first signal, then you will get the Laplace transform of the entire signal. So let me repeat again. If we have a periodic signal like this with time period t, then you don't have to calculate the Laplace transform of the entire signal. Okay, you should have calculated, or you should consider the only Laplace transform of the first signal. Okay, Laplace transform of the first signal. So whatever is the Laplace transform of the first cycle, Laplace transform of the first cycle, then with that answer you must multiply this term 1 by 1 minus e to the power minus st. So if you multiply this factor with the Laplace transform of the first cycle, then you should get the total answer. You should get the Laplace transform of the entire signal. Okay. So what is this actually? 1 by 1 minus e to the power minus st. Now here this t is very important. This t is very important. What is this t? T becomes the time period of the signal. T becomes the time period of the signal. So what is that theorem? The Laplace transform of a periodic function with time period t is equal to what is the answer? It says 1 by this term, this times 1 by 1 minus e to the power minus st times the Laplace transform of the first cycle of the periodic wave. So you need to first consider the first cycle. Whatever be the Laplace transform of the first cycle, you must multiply it with this term, this factor 1 by 1 minus e to the power minus st to get the Laplace transform of this entire waveform, entire periodic waveform. So it is called theorem for periodic function. Now let us consider another important theorem. It is called convolution theorem. If two functions are convolved each other by this symbol, it means convolve. Now what is convolve? This word convolve means to revolve continuously. If two functions are revolving with respect to each other, it means it is convolving. So these two functions are convolving each other, then what will be the Laplace transform? You must multiply f1s and f2s to get the convolution of the two functions. Okay, so this is called convolution theorem. So we have discussed few important properties. Now out of this property, as far we have from our experience, you see this property number 3 are extremely important, property number 4 are extremely important. At least you can get the application, some application, very important application. Property number 5 is important, property number 6 is important, property 7 is important, property 8 is important. These properties are extremely important, and also to some extent property number 9 is also important, and remaining properties you can understand and you can memorize. Okay, so soon we will find their application of these individual properties. At that time it will be clearer, more clear to you. Now we have electrical network. Now we have some now in any electrical network, we have some energy sources, right? So to work properly for any electrical network, we require energy source. So we have different kinds of energy source available. Say for an example, if you consider a battery can be said as a DC source, or you can say AC, that is a sinusoid. Okay, so it can be said as a AC, sinusoid signal. So in this way we have standard variety types of signals, standard signals. Now if you want to apply the Laplace transform to solve the network, transient behavior of the network, okay, that network has got R and L or maybe C. You can apply those differentiation theorem, integration theorem on those parts. Okay, so the voltage drop across the inductor is L di dt, voltage drop across the capacitor 1 by C integration 0 to t I dt. So you can apply those theorems on those things. But what about the sources? So the network also has a source. It is a one of the main component, because other than the source they will not work. So you should know what will be the Laplace transform of those source as well. Okay, it is not actually the Laplace transform of those elements, actually, no. Along with that, you must understand what will be the Laplace transform of those network or those sources as well. We need to modify, or we need to represent different source mathematically. So let us familiarize with some standard signal. Let us say, now in each signal, before starting, let me make a comment that for each signal we shall see two versions. First of all, it's a standard version, and second is a shifted version. Okay. So standard version, by meaning, I want to mean it by that standard signal is one that starts from zero. That starts from zero. It's a standard signal. So a first signal is called impulse. So what is an impulse? Impulse is having some finite value at one point of time, and except that time it has zero. That is why it's called impulse. So at some point of time, at any particular point of time, it has got some magnitude A. Other than that, it has magnitude 0. That is why it is called impulse. So normally, to represent the impulse function, it is represented delta t, that will be is equal to A when t is equal to 0, and it is equal to 0 when t not equal to 0. So it will only have the magnitude for t is equal to 0, and it is having some 0 value or null value other than t is equal to 0. So this is a first standard signal we have. And if we apply the Laplace transform on this signal, the Laplace transform of this signal will be A. So if we have a impulse signal, its Laplace transform will be simply A. It's very important to remember. Now second, we have a shifted impulse. We have a shifted impulse. So it is shifted by some time t is equal to A. Here it is A. So according to theorem 5, it says that time domain shifting means frequency domain multiplication. So it should be multiplied by a factor e to the power minus as. So original impulse A with A magnitude, it has got a magnitude A, that is Laplace transform. So since it is shifted in the time domain, so in the frequency domain it should be multiplied this factor e to the power minus as. So for a shifted impulse for this function, it will be the Laplace transform of this, it will be a to the power minus as. Capital A is the magnitude, that is the Laplace transform of the impulse. However, this additional term, this multiplication term, is due to the time shifting in the time domain. So it is the application of rule number 5. It is the application of rule number 5. Second standard signal is called step. It is actually DC voltage or battery. Okay, it is very important. So what is the definition? It is the definition. It is first of all written as by a symbol UT, capital UT. If it has some magnitude A, with, you see, it is having some magnitude A, it is maintaining, so it is a characteristics of a DC voltage or DC battery for t greater than equal to 0, and it is having some magnitude 0 for t less than 0. So this is the step function, or you can say it is a DC source. So if the magnitude is 1 other than A, then it is called unity step. Then it is called unity step. What is unity step? If a becomes 1. So for such a signal, Laplace transform of a step signal will be a by s. Laplace transform of suppose we have a ut, then its Laplace transform will be a by s. It's very important. So what is the difference with the impulse? It is only a for impulse, but in this case we have some term a by s. So it is the a by s, the Laplace transform of the step signal. Now we have a shifted step. It is shifted by some amount a, so it will be multiplied in the time domain, e to the power minus as. Now next we have a very important signal with us, which is called ramp. What is ramp? Ramp is like this. It is a linearly increasing waveform. Okay. So for this waveform, it is normally written as RT, by represented or symbolized as RT. What is RT? RT becomes A by T into T. Why A by T? Because A by T becomes the slope of this. If this is theta, the slope becomes capital A by T. It is the change of y by change of x. What is slope? Slope is equal to dy, that is change of y by change of x. What is dy? What is change of y? It is a minus 0. Is d delta x? Delta x, it is 0 minus t minus 0. So it will be a by t. So it is, this becomes the at, that is slope, and this small t becomes the characteristics of the ramp signal, a by t into t. So if we apply the Laplace transform of on ramp signal, the Laplace transform will become a by t. Now in the denominator we have a square. In the denominator we have a square. So again, I am comparing three basic signals now. We have first impulse. So if we apply Laplace transform on impulse, it will simply becomes a. It will simply becomes a. Then we have step signal. If we apply Laplace transform, it simply becomes a by s. Now we have ramp. If we apply the Laplace transform, it will become a by t s square. What is a by t? A by t becomes the slope of that function. Now similarly, if we have a shifted ramp, it is shifted by some value a. So this is the product in the time domain, product in the frequency domain. So similar results. Now the next is polynomial. Now polynomial is represented by any function with some higher order, that is n, 2, 3, 4 and something like that. So for that type of function, its Laplace transform becomes n factorial divided by s to the power n plus 1. So this is the Laplace transform of any polynomial function. Now we have a very important, extremely important function, which is called gate function. Which is called a gate function. What is gate function? Gate function looks like this. It's like a gate. It's like a gate-like structure. Now, what is actually this? Actually, so we shall discuss gate function. So it is pictorially, it is represented by this gate like structure. Like in the x-axis we have time, in the y-axis we have some magnitude. Let us say this magnitude is A. So this is A and this is actually B, right? So the gate function is represented by u t minus A minus u t minus B. What is u? U is represented, u means actually it is step function. U means actually a step function. That means it is subtraction of two step functions. Okay, it is subtraction of two step function. Why means actually you can understand. Suppose from A one signal, one step function is generated. It is actually u t minus A. U t minus A. Let us say the magnitude is A. Now from this is so in the first sub figure we have drawn a step function, a shifted step function, which is starting from t is equal to small a, and it is maintaining magnitude of A after t greater than A. Now let us say we have another step function which is starting from t is equal to B, which is starting from t is equal to B, and it is again maintaining that magnitude A. So now if you subtract these two, so it is actually u t minus B. So now if you subtract these two, then you can understand that from 0 to t, from 0 to A, this instant both the functions are 0. That means u t minus A is 0, u t minus B is also 0. So their subtraction 0 minus 0 is 0. Now from A to B, you see this is magnitude A and second function is magnitude 0. So from A to B, it will get A minus 0 is A. So again from B to infinity, so both the function is having magnitude A. So if you subtract them, so it is 0. So in this way, if you subtract two shifted step function or simply two step function, you will get a structure like this. It is called gate function, and mathematically it is represented as this equation. Gate function is nothing but it is a subtraction between two step functions. Now what is the application? It's very important. One very important application of the gate function is that suppose we have a function is like this. We have any arbitrary function is like this. So any random, any arbitrary function ft. Now when you multiply this ft, into this get function g, then that existence of that function will be only existing for the instant up to which the get function existed. Okay, so roughly the existence of that function will be there only for that instant only for which get function is existing. So whenever get function is value 0, so remaining functions is off. That is the reason, because from 0 to A the get function value is 0. So anything multiplied with 0, it is 0. So it is this portion is off, And similarly from b to infinity, again the gate function value is 0, so remaining portion is cut. So only thing is present here is that part which has got the existence of the gate function. So that is the property of the gate function, very important. So if we multiply any arbitrary signal with the gate function, any arbitrary signal of the gate function, so we shall get that function existing only within this limit. Okay, so that is the property of the gate function. Now as I told you that it is the subtraction between two gate function, it is ut minus a minus ut minus b. So if you have a function ut minus a, then its Laplace transform will be a by s into e to the power minus as, because since it is a time shifted function, so it will be multiplied in the frequency domain. And similarly ut minus b, it will be similar expression a by s, it should be multiplied with a e to the power minus bs. So the Laplace transform of the gate function will be a by s into e to the power minus as minus e to the power minus bs. So that is a straightforward formula, gate function. So now very important, mostly known form, it is sine wave. Now if we have a sine wave, then its Laplace transform will be this, omega square by a square plus omega square. And if it is a shifted sign, then it should be multiplied by this factor. So if we have sine omega t, its Laplace transform will be become omega square divided by a square plus omega square. Now secondly most known sinusoid is now coming, it is cosine. So we have cosine. So if the cosine is that, if its Laplace transform is this, s by a square plus omega square, s by a square plus omega square, this is the Laplace transform of the cosine. So similarly if we consider a shifted cosine like this, it should be multiplied with that factor e to the power minus as. Now again a very much important function, it is called rising exponent, e to the power at, e to the power at. Now let us understand what is the Laplace transform of e to the power at. So we have e to the power at, we can write e to the power at into 1. Okay. Now what will be the Laplace transform of 1? 1 can be taken as step. So if it is a step function, let us check what is the step function. Step function will be a by s, where a is the magnitude. So if it is become a equal to 1, then it is called unity step. So if we have 1, its Laplace transform become 1 by s. Okay. If any signal having magnitude 1, that is a step function, its Laplace transform becomes 1 by s. Now let us going back to the theorem, property number 6, this property, multiplication rule. Now you see it is e to the power minus at into ft. Now here for this example you see this is multiplied in the time domain by a factor e to the power minus at. Okay. So if you analyze or if you relate, so it is actually nothing but e to the power at into 1, it is actually multiplication in the time domain. So multiplication in the time domain, that means shifting in the frequency domain. Okay, shifting in the frequency domain by this factor f into s plus a. So please carefully look, when it is multiplied by a factor e to the power minus at minus a, then it is shifted by an amount plus a. So in the time domain, if it is a multiplied by a factor minus at, then it is a shifted by plus a, and when it is e to the power plus at, then it is shifted in the frequency domain by e to the power s minus a. So if it is a multiplied with e to the power at, then it should be, its Laplace transform will be 1 by s minus a. That means multiplication in the time domain automatically transfer or automatically defeats the shifting in the frequency domain. So that is why the rising exponent e to the power at has the Laplace transform is equal to 1 by s minus a. And for the similar reason, if we have the time domain e to the power minus at, then its Laplace transform will be 1 by s plus a. Again I am repeating why, because it is actually e to the power at means e to the power at into 1. 1 is the step signal, so the Laplace transform of the step signal is 1 by s. So since it is multiplied in the time domain, it must be shifted in the frequency domain by a factor a. So since it is a plus a in the time domain, so it is shifted by a minus a. So the result is 1 by s minus a. So now let us quickly go. So suppose if we mix both, now it is called actually damped sine. We know they are actually very important. So let us sine omega t, just we have understood its Laplace transform will be omega square divided by s square plus omega square. Now if we contaminate this sine wave with some exponent function, so let us say e to the power minus at into sine omega t. So what will be its Laplace transform? So again it's the application of this rule. Actually it's a multiplication in the time domain. It is the multiplication of the time domain. Here it is multiplied with this factor. It means we must shift the function in the frequency domain. Then its Laplace transform will be omega square divided by now s plus a whole square. So this is shifted by an amount a in the frequency domain, and finally we have omega square. So this is the Laplace transform of a damped sine. This is called damped sine wave. So if it is a contaminated with a exponent, it is called a damped sine wave. Similarly, we have similar equations for a damped cosine. So if it is a contaminated with a decaying exponent, so it is called damped cosine or damped sine, whatever it may be. So for a cosine wave, its Laplace transform will be s by s square plus omega square. So if it is contaminated with this factor e to the power minus at cos omega t, then its Laplace transform will be s plus a. That means shifting in the frequency domain. So in the denominator we have s plus a whole square plus omega square. Now similarly, if we have e to the power minus at into t. Now what is t? T is actually 1 by a square from the ramp. Right? You see, this is ramp. This is ramp. If a by t is equal to 1, then it becomes only t. Okay. If a by t becomes 1, it becomes only t. So if you is only ramp, that is called unity ramp. If it is only t, then it is called unity ramp. So then Laplace transform of a unity ramp is only 1 by s square. So if it is contaminated with again the damp the decaying exponent, then it will become 1 by s plus a whole square. That means s to be shifted. Okay, not the overall function should not be shifted as a whole, but s, that s term should be shifted by that amount. So we have seen few important properties and its application for some signals, standard signals. Okay, we have seen differentiation rule, integration rule. Then we have seen two important properties, that if we have a function in the time domain and if it is a shifted in the time domain, that means it must be multiplied in the frequency domain. There, following to that, we have also seen that if a function is multiplied in the time domain, then it must be shifted in the frequency domain. Then we have seen initial value theorem, final value theorem. Also we have seen the Laplace transform, what is the rule of a Laplace transform of a periodic signal, and we have seen some standard signals which we will use as an energy to feed any electrical network. And also we have seen what will be the Laplace transform of those standard signals. So with this, let us end this discussion here and continue discussion on this topic from the next session. Thank you.